Good morning friends. Next our topic is reactive power for star and delta. So first we are going to discuss about reactive power in star load. Okay, this is the actual circuit in delta load reactive power. Okay, so according to that circuit we are going to connect the circuit control panel here. Okay, so active and reactive power for star and delta loads. Already we discussed active power for both star load and delta load. Then we are going to discuss about reactive power for star load and delta load. First we are going to discuss about reactive power for delta load. Okay, so according to circuit we are going to connect it. First you have to remember R phase we are directly connected to voltmeter, and then from voltmeter to ammeter, and ammeter to directly we are connecting wattmeter M, and here wattmeter M and C shorted. Okay, then again L is connected to wattmeter, varmeter M. So you remember here one important point is here this one is a wattmeter and this one is a wattmeter and this one is a varmeter, but this varmeter is not working in this control panel. Because of that, for varmeter replacing with wattmeter. So in this, by using this wattmeter I am going to convert into a varmeter. It's mean whenever we need to convert this wattmeter into varmeter, so by using without MC short, then this wattmeter will be converted into varmeter. So this varmeter is useful to measure the reactive power. Okay, so the difference is nothing is there. So everything is same in active power, star load and delta load, everything all the connections are same, but the difference is, you remember here in this circuit, so in active power and active power, star load and delta load already we done, we given connection also, the same connections here also, wattmeter 1 and wattmeter 2. But externally here in this reactive power we can get it varmeter. Other than that, remaining this entire connection in active power and reactive power is same. So same voltmeter and ammeter and wattmeter 1 and wattmeter 2. But the difference is externally we are taking one varmeter in reactive power for a reactive power measurement. Okay, so here this varmeter M is connected to wattmeter L. Okay, so you remember this wattmeter L is connected to M of this varmeter. Okay, and then next this varmeter L is directly connected to resistive load R. So here L is there. Okay, that L is directly connected to R load of the delta load. Then next V is directly connected to B phase. Here V is directly connected to B phase. This V, varmeter V is directly connected to B. You remember here we have three voltages. This one is 150, this one is 300 and this one is 600. But here we are going to take it 440 volts. So 440 volts 150 into 4 here. So it's mean 150 into 4 in the sense we can get it 600 almost. Okay, here according to this connection. Okay, so we will discuss later how we are connecting the wattmeter, these two pins. So how we can connect it, we can get it the current value and voltage values. We are going to discuss in a separate video. So you remember. So in this wattmeter, directly V is directly connected to B phase, B load, not a B phase, B load of the delta load. Okay. Then next here C is there now. So in wattmeter we are going to shorted MC, but in varmeter we cannot short the MC. So that C is directly connected to Y phase. So this C means it's a common terminal of the wattmeter, that varmeter. So that one is directly connected to Y phase of the load. Okay. And then here you remember B phase is directly connected to wattmeter to V, and Y is directly connected to Y phase, and here R phase is directly connected to voltmeter. This is the actual way of connection of reactive power delta load. Okay, you remember. Then we are going to start the experiment. So I am going to turn on main supply MCB, and then I am going to vary the variac up to 400 volts. So you remember here 400 volts. So in no load condition, for 400 volts 0 current, and wattmeter 1 also 0 and wattmeter 2 also 0, and as well as varmeter also showing 0 value. Okay. Then I am going to apply the delta load. Okay. Whenever I am going to apply the delta load, then I got all the readings. You remember for 400 volts I got current 2.35. That 2.35 I have noted down here, 2.34 or 38. Okay, noted down here. In first wattmeter we got approximately 500 watts. So that 500 watts I have written here, and second one you remember 750 watts second wattmeter reading, that 750 watts mentioned here. And then you remember here totally approximately I got it 98 watts. So previously I have taken value, that value is 102. So that's why I have mentioned here 102. But in wattmeter we connected pins, no. So based on that pins 102 into multiplication factor 4. Because of that var voltage we can get it. Sorry, var value we can get it 102 into 4 times of that value. It means the range of meter is 150, 300 and 600. We connected for a 300. So whatever the reading we can get it here, that reading into multiplication factor 4. Okay. So that one I mentioned here. Okay. So next part, calculation part. According to calculation part, we can calculate pi value and power factor value and 3-phase reactive power. So first we are going to discuss here, you remember tan inverse root 3 W1 minus W2 by W1 plus W2. Okay. And then tan inverse of root 3, whatever the values we got it here in a load condition. So the values we can substitute here, 500 plus 750 by 500 plus 750 equal to, we can get it minus 19.106 value. Then we will go for calculation of power factor. So this value we can substitute here, then we can get it here 0.86 or 87, 89 something we can value we can get it. Approximately we can get it 0.9 something like that. So this one is a lagging power factor. So 3-phase power, reactive power also we can get it approximately 400 something we can get it value. Okay, you remember this one. So we will go to calculation part. So This is the main thing. So here we can get it, power factor is lagging power factor. So that's the reason only this experiment is right. So why? Because here we have taken inductive load. Okay. So inductive load case always, so in inductive load case always power factor we can get it lagging power factor, because in inductive load current is lagging with the voltage value. So whenever we done the experiment, so that experiment we can get it power factor is lagging power factor, in the sense we done the experiment is right. So for inductive load, if suppose for example we are taking this delta load condition capacitance, in the sense we can get it leading power factor, then only the experiment is right. Okay. Here we have taken inductor, no? So that's why this inductor always shows the lagging power factor only. We can get it in calculation power factor or lagging power factor, then the experiment is right, or otherwise the experiment is wrong. It's mean we done wrong experiment. Then we are going to discuss about calculation part. So for 400 volts load condition, we got current value 2.38 amperes, and first wattmeter reading is 500 watts and second wattmeter reading is 750. So wattmeter we got 102 into 4 multiplication factor, then we got 408 watts. So according to this pi formula, the same formula, whatever the formula we have taken in active power star load and delta load, the same formula we are taking here, tan inverse of root 3 W1 minus W2 by W1 plus W2. So the value, whatever the values we got it, that values we are replacing here, root 3 into 500 minus 750 by 500 plus 750, that is equal to, we got minus 19.106. So that minus 19.106 we can substitute here in, we got it power factor approximately 0.91 or a 0.94 lagging power factor, we got it. So why here we got lagging power factor, in the sense this one is a inductive load. So in inductive loads always we got lagging power factor, because current lags with the voltage in inductive load. Okay, 3-phase reactive power. So the formula is root 3 into VI II into sin pi. So that value we can substitute root 3 into 400 volts. So we have taken input voltage, and 2.38 we got it current value, into sin value we have to take directly sin minus 19.106, that one also right, or otherwise you have to calculate from the cos value. So already we got cos value is 0.91 or a 0.94 something. So that from that value we can get it pi equal to cos inverse of 0.91, in the sense we can get it pi value is 24.49. So that pi value 24.49 we can substitute in sin value, we can get it 0.41. That 0.41 you have to substitute here, then you can get it 683.53 watts. Okay.